So our discussion today is focusing on what we call centrifugal pumps as well as the Pelton wheel. But our introduction will first of all discuss what is the importance, what is the function of a pump, what is the function of that Pelton wheel or rather a turbine, and then we go into the analysis. So this is what we are having for today. Let me take us straight to the first slide so that we get started. So that's our topic, pumps and the Pelton wheel. And this time we'll just sample the analysis of centrifugal pumps. So here, there are so many types of pumps, but for a start, we may ask the main question as to what is the function of a pump? A pump is basically used for helping us deliver fluid from one point to the other, for creating flow in a fluid system. So that's where you put a pump. Unlike a turbine, which will use the moving water and create kinetic energy, this one you already have a rotating mechanism which you are using to create flow or to move fluid from one point to the next. In a centrifugal pump, we use the centrifugal force because the impeller will be rotating at a particular speed, and that centrifugal force is used to push or pump the fluid from one point to the other, meaning from the suction end to the delivery end. Then we also have, of course, we have many other types of pumps. We can have screw pumps, gear pumps, vane pumps, piston pumps, many of them. But this time our focus is just on the centrifugal pump. Now, this is a typical example of this pump which has been installed in a system. Now, what you can see here are the various parts. From here, the flanges, the impeller is here. Then we have this side, which is the delivery side. This is our delivery pipe. This is our suction pipe. And this is our water table, or simply the liquid where we are pumping it from. It could be any other liquid. It could be oil. It could be something else. But this is a typical example of some liquid which we can be pumping. Now here we have various heights, or we call them heads. The first one you can see is this distance from the water table to the center of the impeller. We call it the suction head. Then the other one, running from the center of the impeller all the way to the delivery end, that is our delivery head. Then when you add the two, you have what is known as the static head, delivery head plus the suction head. But we also need to take care of the losses. So we have what is known as the loss of head in the suction pipe. So this is our suction pipe. We basically include a small height going into the water. So that is HFS. Then also in the delivery pipe, we're also going to experience some loss. Remember last time we discussed the loss of head in pipe flow, and the major contributor to these losses is the what we call the friction, apart from these other minor losses. So that loss of head in the suction, then we also have another loss in the delivery. So when you add all these, you add HFS, loss of head in the suction head, the delivery head, including the loss of head in the delivery head or in the delivery pipe, you have what is known as the manometric head. But for calculation purposes, there's one more thing missing, which is the kinetic head, because when this water is coming out, it will come out at a particular velocity. So what do? We add it as well. Now here, this is all we have. We have this representing the manometric head, then plus the additional, which is V squared over 2G. Let's talk about efficiencies of a pump. You introduce these efficiencies to measure the performance of a pump. How is a pump operating? Is it efficient for this fluid system, or do we need a different pump? So first one is the overall efficiency, which is the ratio between that useful work and the energy that has been supplied to the pump. Basically, it's like the work output over the work input. That's how we write the formula. Useful work over the energy delivered to the pump. Then we have what is known as manometric efficiency. So with this one, remember we had a height which we call the manometric height. So we're saying this is the ratio between the head rise, like the manometric head, through the pump, and energy per unit weight that is given to the fluid in that impeller when the pump is working, when the pump is running. So there we are. Head rise through the pump over energy per unit weight given to the fluid in the impeller. So here, this is our HM referring to the manometric head divided by U2 W2 over G. Mechanical efficiency. So with this one, we're talking about the energy, the ratio of that energy, or the ratio between the energy per unit weight that the fluid receives from the impeller and the mechanical energy supplied to the shaft of that impeller, which is running and helping the fluid to move. So we just write it in that short format: energy per unit weight given to the fluid by the impeller over the mechanical energy per unit weight supplied to the shaft. We briefly talk about multi-stage pumps. With multi-stage pumps, it means you have various stages of the pump. The idea is to increase the overall output. So you can have them connected in series, or you can have them connected in parallel. When we connect them in series, it means we're trying to increase the output, because it means one pump will go and deliver the fluid into the next pump, and so on. Then we can also decide to connect them in parallel. Here, it could be the same height you're dealing with, but the output, the rate of flow will be increased, because you have a series of pumps, a number of pumps that are pumping fluid from the same source and then delivering it to one reservoir, or to one end where it is being collected. Next, we talk about the Pelton wheel. Now, in a Pelton wheel, we're discussing the turbines. Turbines come in many forms, but one thing that is critical about them is that, unlike a pump, with a pump, you already have kinetic energy, then you're just converting that kinetic energy to flow energy of a fluid. But with this one, you have fluid that is running it at a speed, and then it will hit against the blades of your turbine, or perhaps the vanes of your turbine, and cause that turbine to move. So you have, in some cases, you could have, like in this Pelton wheel, water could be falling at from a particular height. Then it's directed to the various buckets. Inside the buckets, you have the vanes which are splitting the water. Then the water, when it is redirected through some angle, it will have some resultant force. So what happens after that is that this energy, this force, the resultant force, is then transmitted to the impeller. Now, this is the impeller which is connected to the generator, and then you have electricity being generated because the rotation is now available. So what do we have in a Pelton wheel? With a Pelton wheel, like you can see, we have, first of all, you can have a nozzle. You have the buckets. Then this is our impeller. Now, to ensure that we have a jet striking the water at a particular speed, that's where you may have the water coming there. I mean, the nozzle is shaped in a way that allows velocity to be quite improved. Then that is the one which will strike those buckets and start causing the movement. Then when you want to reduce the speed of this impeller, you use a brake nozzle, which will allow water to come from the opposite direction and hit the buckets in the same opposite direction, opposing the motion, then this will stop rotating. Whatever water is coming from there is collected in the discharge. And of course, this is delivered away. Okay, now here we want to talk about we start with, first of all, the delivery. You will notice that when water is falling from a height, to know how much velocity is being delivered, you use this formula, CV equals CV square root of 2GH. This CV is coefficient of velocity. But then, this is a very common formula, which I think comes from Torricelli's theorem. And when you do this, there are some cases where coefficient of velocity may not be provided, meaning you're just dealing with a theoretical velocity, and you can still go ahead and use it like that. So your V will just be root 2GH. But to get something close to the real velocity, to reality, you have this CV in front, then square root of 2GH. That is the velocity at the point where this water is being delivered to the buckets or to the turbines for them to start rotating. Right, so on average, it's expected that the CV can be between 0.97 to 0.99. Yeah, for this type of a machine. This is the bucket we're talking about. Inside those cups, inside those buckets which are connected to the impeller, this is the shape you have. And as you can see, you are going to deliver the water through this angle. Redirect the movement of the water. Spin it through that angle. As you do this, because it's no longer moving in a straight line, you're going to have a resultant force on this side as well as on the other side. Now, because they are combined like this, the combination gives you that movement. So U itself refers to the speed of this bucket. And it will, of course, have its own value. Then you have two velocity triangles. There will be the inlet velocity triangle as well as the exit velocity triangle. For a Pelton wheel, this is straightforward because the inlet velocity triangle, this is all you have. You have the actual absolute velocity of the water as it is coming from the nozzle, V1. U is expected to be the one we talked about, the velocity of the bucket. VR1 is the relative velocity of that water. So when you come this side, you have the same thing. Our V2 is the velocity of the water, the absolute velocity of flow of this water as it is passing through the vane. VR2 is the relative velocity of water on exit. Of course, this is the exit side. U, like we said, this is the velocity of the bucket. So if you talk about the angle between the velocity of the bucket and the velocity of flow of the water on exit, this is the angle theta. But the relative velocity of water on exit and the velocity of the bucket, the angle they make is alpha. Now, interestingly, what you have there is a right angle triangle. So you can definitely start referring to that one. Okay, this is still talking about the same thing, mean bucket speed. So how do we determine the force exerted on the bucket? This takes us back to what we've been seeing in this part of our subject, which is Newton's second law of momentum, where we say that the force is supposed to be equal to the rate of change of momentum, the resultant force. So here we say mass deflected per unit time multiplied by the change in velocity of the bucket. Mass deflected per unit time is going to be given in kgs per second. The change in momentum, or rather the change in velocity, is going to be just the difference in the velocity. So U minus the other velocity. But then what you will realize is that the final velocity in the direction of motion, the component is this, V2 cos beta, V2 cos beta. Leave it like that. Then let's go to the change in velocity. Then the change in velocity is supposed to be V1 minus V2 cos beta, so that we're able to see how much change we have there. So with this, we can now do the analysis. We're saying the mass, this mass, is supposed to be density multiplied by the discharge. When you multiply density by discharge, the volumes cancel out. Then you remain with the kgs per second as it is shown here. Then what we are talking about here as the change in velocity is this component here now, which is V1 minus V2 cos beta. V2 cos beta. Then let's go back to the efficiencies of a Pelton wheel. Just like we had with a pump, a Pelton wheel also has efficiencies. We have what is known as the hydraulic efficiency, which is the ratio between the work done on the runner, the unit weight of the fluid, and the available head. What we are calling the runner is that central mechanism rotating, in this case, the packets around. So there we have it, work done on the runner per unit weight of flow over available head. Traditionally, we express these efficiencies in percentage form. So that is in multiply this by 100. Over efficiency, here we're talking about the over efficiency of the whole mechanism. So that gives us a ratio between the work delivered to the shaft per unit weight of the fluid or flow and what is available, the available head. And of course, this is always supposed to be expressed as a percentage as per tradition, but sometimes you may not multiply by 100, you will leave the formula like that, meaning that the answer you will get, you don't put the symbol for percent, you just leave it like that. We also have what is known as mechanical efficiency. So the mechanical efficiency, that is the ratio of the work delivered to the shaft per unit weight and the work done on the runner per unit flow weight, meaning per unit weight of what is flowing. And of course, we also express it as a percentage. Here's our example. We'll starting with a pump. So with the pump, we have an impeller whose external diameter is 450 millimeters, internal diameter 200 millimeters. The speed at which this impeller is running is 1440 RPM. And then we're told that the flow through the impeller is at a rate of 2 meters per second. Vanes are curved back at exit with the angle 25 degrees. Then we need to determine the inlet vane angle, the angle between the absolute velocity of water and the exit. Then also the work done per unit weight, of water. Those are the parameters we need to calculate. So what do we need to do? Deliberately, here we are going to pick one vane inside the impeller and analyze it because it's going to have inlet velocity triangle and an exit velocity triangle. That is where our parameters are hidden, and we'll analyze from there and proceed. So here we have our D, the diameter of the impeller, the external diameter of the impeller. We thought it's 450 millimeters. We cannot leave it in millimeters. It has to be in meters. So that's why we divide by 1,000. So we get 0.45. And 450 divided by 1,000, 0.45 meters. Rotational speed was given as 1440 RPM. Then here is our U2. Velocity of the vane, exit velocity of the vane, that's U to the absolute velocity. So with this one, we're going to use the parameters given, the dimensions that have been given for the impeller on exit We know that the exit diameter or the external diameter of the whole impeller is 0.45, and meaning that if we now have to convert the U2, it's pi dn over 60, because this is, we are converting something like V equals omega R. Moving backwards, then this is the shortened version by dn over 60. So where there is d, we put 0.45, and this is 1440, then over 60. Then we get the 33.9232. Next, we have small letter d, which is 200 millimeters. So this is in 200 over 1000, which gives us 0.2. Again, we use the same formula, but we introduce small letter d. So pi dn over 60. Here we put 0.2 and the 1440, then this is the 60. So your U1 comes out as 15.0796 meters per second. Now, let's get this straight. Take you back to the question so that you can understand what this one is saying. It says, allows for a constant radial flow through the impeller at 2 meters per second. What is the meaning of this statement? It's what we have written here. The velocity of flow at inlet, this is VF1, is equal to the velocity of flow at exit. So VF1 is equal to VF2. The relative velocities are the same. Oh, sorry, the relative velocities are different, but velocity of flow 1 and 2, according to the information provided, these are the same. If they are different, the question will verify, it will state, and you use those numbers as they have been provided. Then check back again. We're told that on exit, the vanes are curved back at an angle of 25. So if you go back and take the tangent of this vane, then make with the horizontal, what you get is the 25 degrees that was provided. So that is the angle there, 25 degrees. Then you have V2, the absolute velocity of water on exit. Then this is the one we're talking about, the velocity at exit, basically the velocity of the impeller on the vane rather, on the exit. Just like the other one, it was the bucket, but this time it's the vane. These are different. For the U1, it's smaller. For the U2, it's bigger because there, the diameter we're dealing with is bigger. Then you also have the velocity of wheel, which is BW2 here. If you check the triangle that we are having here, we do not have this shape. We have V1, which is equal to velocity of flow 1. The absolute velocity of flow is the same as the absolute velocity of the water is the same as the velocity of flow into the vane. So that's why the velocity of wheel is 0 here. Then there, the velocity of wheel is definitely going to be that one, which has been created in the corner. All right, now, the secret to all this is simply this triangle we've drawn here, this vane we've drawn here. Once you've done this, then you can start your analysis and you can start working backwards. But let's look at the way information was given. What did we need to find? First, we need the inlet vane angle. The inlet vane angle. Which is our inlet vane? Inlet vane angle is theta. This one here. So that the angle between relative velocity 1 and absolute velocity of the vane 1. So this is our theta in the corner. When you look at this one, you already notice that we we have these two here. If I say V1 over U1, I get tan theta. Or if I decide to use these two, I can easily say U1 over VR1 is supposed to be able to give me sine theta, or this V1 over VR1 to give me, I mean, this one, U1 over VR1 is cos theta, whereas V1 over VR1 is in sine theta. Whichever you do, all we are running around here is simply the SOHCAHTOA, just the basic trick. So here I have it. V1 or VF1, because V1 is equal to VF1 over U1, we said it's tan theta. So V1, which is VF1, we told it's 2 meters per second. And U1, we calculated it as 15.0796. So this gives us 0.13263. So what we want is the angle theta. So we say tan inverse of 0.13263, which gives us 7.555 degrees. What about now the angle between the tangent? Let's go to part B. B was asking for the angle between the absolute velocity of the water at exit and the tangent. So with this one, we're looking at beta, or we call it beta. So with beta, first of all, you need to find velocity of VW2. And this is the one we said you need to do some mini, let me just take you back to this one. We are talking about this one. Because V2, we don't know it. What we do have is VF2. VF2 is the same as VF1. So we will say VF2 over VW2 to get tan beta. Tan beta, this one here in the corner. To get it, you need this velocity of flow on exit divided by velocity of flow on velocity of wheel on exit. VF2 divided by VW2. So then you get tan beta. So meaning that this, we do not have it, but this one we have. And even VF2 we have. So you notice here that there are some, we just need to come up with a way of finding this one. So how do we do it? It means that at least even if we don't know what this one is, we can subtract the whole of this length minus this distance from here to there. Let me just pick a pen quickly. If I pick this pen, I'm talking about this distance here. Oh, forgive my line there. This distance, I can decide to call it, give it a letter like X, for example. Let me give it as X. So what I'm saying is that if I want VW2, I should say U2 minus X. So it's U2 minus X. So I write there U2, take away the X which I've just found here. But if you look at the shape, this triangle I have here, I already have an angle here in the corner, which is 25 degrees. And I also have VF2. How do they relate? If I consider the ratio between VF2 and X, it's tan. So I can say that tan theta, my tan theta, forgive my handwriting again. My tan theta is supposed to be equal to, we're saying VF2, VF2, everything divided by X. Why VF2? One, because VF2 is opposite that angle. We always say that tan is opposite over adjacent. So VF2 is opposite, X is adjacent. And so what I want is X. What I want is this X. If I want to make X a subject, it means they will just switch. So I will have x being equal to VF2 over tan theta. So that's now my VF2 over tan theta. So that becomes my, over tan theta. Everything divided by tan theta. Now, look at where we're coming from. If you check what I have here, it's VF2 over tan theta, meaning that if I come back to this, in this case, what I was actually looking for was VW2. VW2. So why not go back and substitute for this? So what I have now is this. I'll have VW2 being equal to U2 minus this thing I've written here. U2 minus VF2 over tan theta. So let me take us back to there. This is what I have. So then VW2 equals U2 minus VF2 over tan, rather not alpha, not theta, but the alpha, which is 25. So here, then I have VW2 is equal to 33.9292 because U2 was this number here, 33.9292 meters per second, minus, then VF2 is 2 meters per second divided by tan 25 because my angle here was actually 25. Let me just remove that because it could be disturbing, it could be standing in the way. All right, so this is what I have now. And here, when you enter this in your calculator, you have 29.6402. That's just VW2. So that gives us a complete package now. Then tan beta is equal to VF2 over VW2, meaning that 2 over 29.6402. This is the ratio. Then tan inverse of this gives us 3.86 degrees. That is now our angle between the tangent and the exit absolute velocity. The absolute velocity on exit. So that's what we have now as our angle referred to as beta there. Last one was asking for the work done per unit weight. The work done per unit weight, the formula is simply 1 over G VW2 minus VW1, because this is per 1 Newton. So you go back, you notice that VW1 was 0, whereas VW2, we just found it to be 29.6402, then 1 over 9.81. Your answer is 3.021 joules per Newton. I think this one was just some typo in the unit. So that's our answer for the work per Newton, joules per Newton, work per unit weight of that fluid. Let's pick up another one. This time we're dealing with the Pelton wheel. With the Pelton wheel, we have this example where we're told that the rate of flow, the water is being supplied from this height, 30 meters, at this rate, 41 cubic meters per minute. Then deflected through this angle of 160 degrees. And the mean bucket speed is 12 meters per second. Let's find the power delivered to this turbine and the hydraulic efficiency. So we start again. Our head is 30 meters, velocity 1. To know how much velocity we are having when the water is just coming out after it has been delivered, we use this formula. Like we had said, in this case, we don't have the coefficient of velocity, so we just say 2gh, no problem. So 2 by 9.81 by the head, which is 30. So we have 24.261 meters per second. This is now the bucket speed, 12 meters per second, theta, 160. So if you talk about the alpha, it's the difference between the theta and 180 degrees. So you have 180 minus 160, you get 20 degrees. Density of the fluid, 1,000 kg per cubic meter. The discharge is 41 cubic meters per minute. So 41 cubic meters per minute. Now every minute has 60 seconds. So you convert that to cubic meters per second by dividing by 60. So this is what we have, 0.6833. Now let's go back to there. The force exerted on the bucket, we said it's supposed to be equal to the rate of change of momentum, where we said density, discharge, then V1 minus V2 cos beta. Do we have all these? Yes, but let's pick them one by one. So first of all, we said V2 equals V2 cos beta is the same as Z. Then we dive into this because we will need to find the equivalent. So this is the same as U minus V1 minus U cos alpha from the shape or the angle given. So now what do you do with this? Since this is the case, so it means that I have to go back to that formula and rewrite it. You will notice that all we are tampering with is this second part because the inlet values are the ones we have. So what are we going to do? Then we also told the relative velocity is the same because this one has no friction. So that remains like that. So we have density times discharge. Then we bring down the V1. Then what I have now is U minus then V1 minus U cos alpha. But then I can decide to open these brackets with just this one. So if I multiply this by that, I'll get a positive. But U times negative multiplied by the positive, I have minus U. Then plus, negative times negative, that's a plus, positive. Then the rest remain like that. And then we can now go ahead. One thing you will notice is that I have V1 minus U. I also have V1 minus U, which makes it common. So it's like inside here internally, away from this, I can factorize where I'll put this in the brackets. Then I'll have 1, then there's plus, then there's cos alpha, meaning I've just decided to factorize there. Now, here's one thing I can assure you. You may not need to travel this far. You can start replacing right here and you'll still get the same answers. But this extra step we've taken is just to simplify so that when you are working, you minimize those mistakes. So you have density times the discharge. So the density 1000, the discharge in cubic meters per second is 0.6833. V1 rather, we're told is 24.261 minus the velocity, we're told it's 12. That is the absolute velocity of the bucket, which was 12 meters per second. Then we also have 1 plus the cos 20, the angle that we just found. When you enter all this in your calculator, your force will come out of 16,251.42 newtons. 15 to 51.42. Let's go for the power. Power, because we've just found the force, power is force times velocity. How? Let me just quickly illustrate in case. Remember that we say power is work over time. That's the definition. The rate at which work is done. That's power for you. Now, when you look at this work, work is the force multiplied by distance. So distance, I may decide to use the displacement. or simply D, but this time I'm deliberately using that. So if you notice, when I say displacement over time, the rate of change of displacement, this whole part here is velocity. So in this case, we're using velocity is U. So we're going to have F, which is the force, multiplied by that velocity, the velocity which is U. That is how come we have this simplified formula there. So we're just going to substitute now this, and we're talking about the power delivered to the bucket. So that's why we're going to use the velocity of the bucket, the absolute velocity of the bucket, which was given us 12 meters per second. So the force 16,251.42361, I multiply this by the 12, and the answer I get is this. So there I have it. That's the power being delivered. Let me just take you back again. Here the question was asking for the power delivered by this turbine. So the power delivered by the turbine, that's the one we found now, 195,017.084 watts. For those of you who are very familiar, those of you who like kilowatts, you can convert it, 195.017 kilowatts. But my advice, if you haven't been told to convert to a particular unit, leave the answer the way you found it and stop stressing, because you can now eventually make a mistake as you try to refine it with your conversions. Let's pick up the last part. We're told to calculate the hydraulic efficiency. For a Pelton wheel, the hydraulic efficiency, we said, it's simply this power output divided by the available power or power supplied. So what do we have? So the power output is this one we just found, which is rather, that's for the available one. So power output 16,251.42 times 12, meaning if you want, you can just lift this number the way it is and you plant it there. What about the available power? The available one, you multiply the density by the discharge, by gravity, by the available head. Because this whole formula here can give you the amount of power that a pump can work against. So density by the discharge, by acceleration due to gravity, by the available head, which is h. In this case, we were told that h is 30 meters. So my density, because I'm dealing with water, my density is 1,000. The discharge, water coming out from the nozzle there is at 0.6833 cubic meters per unit time. And this G is 9.81. Then this is my 30. Whichever version of calculator you have, as long as you use it correctly, it's supposed to give you your hydraulic efficiency, in this case, 97.097%. 97.097%. You will notice here that the efficiency is quite high, but of course we still have some losses, and it's normally not possible to reach 100% for real machines. Well, I also have for you an exercise here combining. The first set is for pumps. The second set is for turbines. Total 6, so 3 for each. And the answers have already been provided for you to do the try out exercise and see how all that comes out. So see anything that requires my attention, post in the comment section or reach out to me, and then I'll get back as soon as practicably possible.